Okay, this is the Module 3 review, and our first slide is problem number 1, where we are being asked to complete an appropriate table and use your table to list the key features using appropriate notation of the relation below. So the relation is this recursive formula right here, f of 1 equals 3, and f of x equals 4 times the previous output, f of x minus 1. So let's do a table. Okay, now in a table, or some people like to call this a T-chart when it's vertical like this, in the left column we will place an x, and in the right column we will place our output f of x. And if you look at our recursive formula, I'm sorry, my dogs are having a lot of fun in the backyard. I hope they're not disturbing you. All right, this 1, that's going to be my first x value in my table. And then my x's, I'm just going to increase them by 1. So 2, 3, 4, and so on. That will go on forever. Now, my f of x's, well, f of 1 is 3, so my first f of x is 3. When x equals 1, f of 1 is 3. And that's what that says up there. And then the next output, well, is the previous output times 4. So 3 times 4, 12. That's right, that's a common ratio of 4. So I'm just going to multiply my output by 4 every time. 12, and 12 times 4 would be 48. And 48 times 4 would be, what's that? 100, let me see, 40 times 4, 160, and then 8 times 4, that's 192. And, you know, again, if you need to get a calculator out, do so, please. And so on. Okay, so there's my table. There's the first part. Now, use your table to list the key features using appropriate notation of that relation below the recursive formula. So, first thing is this a function? Yes or no? And now, you don't have a graph, so you can't do the vertical line test, but with this table, do you agree that every input has one and only one output? And in a table I look, do I ever have the same input twice anywhere? No, I don't. So every input has one and only one output, so yes, that relation is a function. And then what's the domain? Well, for the domain, we're talking about our x values. X is in, and you don't have to write this part, but you do have to now use the appropriate notation. All right, and again, this is a recursive formula. That is what they started us with, and they didn't tell us anything else like that. This is a recursive formula for a continuous function, so we have to assume that with that recursive formula, this is discrete. So instead of interval notation, we must use set notation. And now you just list your x values for your domain, because the domain is what? All of the x values in this function. So my first x value is the 1, and then the 2, and then the 3, and they only gave me room for one more, so I can't put 4 there, but I can see a pattern, so I'm going to go dot, dot, dot right here. 1, 2, 3, and so on. That pattern will continue forever. Now the range. Well, that is all the y or f of x values. So I'm just going to say y in for my range. Set notation again, and my first y or f of x is a 3, and then a 12, and then a 48. And I'm not going to put 192 here because I have to talk about this goes on forever. So here I'll put my dot, dot, dot. And again, I just have to have enough terms so everybody can clearly see a pattern. My x's are increasing by 1, and my y's are being multiplied by 4. Now the extrema. Is there a max or a min? And you don't have to write this part down, but you do have to give me any extrema you see as an ordered pair. Well, the smallest y I see is a 3. All right? But notice, what's the max? These f of x's or y's are just getting bigger and bigger and bigger. So there is never going to be a maximum. So for the max, you would just put the empty set, because these ordered pairs are just going to go on forever. The y's will get bigger and bigger and bigger. But there is a min because the smallest y I see is a 3. So I'm going to write this x equals 1, y equals 3 as an ordered pair. X is 1, always put your x first, and then your y, 3. Now, f is increasing on. Okay, well, when is this function increasing? Look at your f of x's. It's increasing within its entire domain. So again, I can just rewrite my domain like I did up above there. Okay, now, when is it decreasing? Well, the f of x's or the y's are always getting better. This function is bigger. This function is never decreasing. So that's going to be x is in, and the part you have to write is the empty set. Now the y-intercept. Well, at the y-intercept, x has to be 0. And x is never 0, so there is no y-intercept. The x-intercept. Well, at the x-intercept, y would have to be 0. And y will never equal 0, so that is also the empty set. And that's our first problem right there. You need to be able to look at a relation in whatever form they give it to you in, and maybe create another model, and then use that model to come up with the key features of your function. Okay, number 2. Excuse me. List the key features using appropriate notation of the relation below. So this time the relation they have given you is a graph. And they did not ask us to model it in any other way, so we're not going to need a table or formulas or anything like that. Now, if that would help you answer these questions about the features of this relation right here, then yeah, go ahead and model it another way. But if I have a graph, my first thought is this the graph of a function, yes or no? And again, a vertical line test with a graph, I can just use the vertical line test. So I visualize a vertical line going through the graph. And I think to myself, is there anywhere I could put that vertical line that would cross that graph at more than one point? And no, there's not. So that means every input x has one and only one output y. And that's the definition of a function right there. This graph is the graph of a function because it passes the vertical line test. Now the domain. Well, the domain would be all of the x values on this graph. So x is in, and this is the part you have to write now. Now think about this too. This, unlike number 1, is a solid line. It's a continuous function, so we need to use interval notation. Whenever you have a continuous function, your intervals are all given in interval notation because it's just not a set of numbers, it's endpoints and everything in between. So here's what I like to do here. Interval notation. I like to start with my comma, and then I think, what is the minimum x value on this graph? Think about how far is that graph going to work to the left. Okay? And you see this arrow down here, right? It's going, I know that looks like it's going down, but it's also working to the left forever and ever and ever. So the minimum x value is approaching negative infinity. And if you have to type this on Google Slides in a test, you don't have that fancy infinity symbol right there. So you just go minus 0, 0. That's how people do that on a typewriter. Remember that. Now, also look at the arrow up here. This graph is going forever up, but it's also working to the right forever. So to the right, x is approaching positive infinity. Now you need to think to yourself, do you need a parenthesis or a bracket? Can x ever reach negative infinity? It cannot. If there was an endpoint, I'd put a bracket. But we can't reach negative infinity, so that's got to be a parenthesis. And to the right, the same thing. x is approaching positive infinity. I can't reach positive infinity. There's no endpoint, so I have to put parentheses. If there had been an endpoint, like let's say this graph went as far as x equals 3, I would have gone 3 bracket right there. Okay, now the range. Those are your y's. Now this is easy because it's the same thing. Okay, comma, interval notation. What's my minimum y value? I don't know because we're approaching negative infinity. To the right, what is my maximum y value? I don't know. So we're approaching positive infinity. It's just going forever. And once again, we cannot reach negative infinity. So you've got to go bracket or parenthesis, excuse me. And we cannot reach positive infinity. Bracket on that side. Okay, had there been an endpoint, oh, and I said bracket again, that's a parenthesis. Had there been an endpoint, we would have used brackets. Okay, Extrema. Well, again, for Extrema, you're focusing on your largest y value for a max and your smallest y value for a min. You're looking for max and min, and you've got to write those as ordered pairs. Unfortunately, what's the biggest y value? I don't know because this is approaching infinity. Therefore, a max does not exist. It's the empty set. We're just going forever and ever. We never reach a max. The same thing for the min. We're going down and down and down forever and ever and ever. We never get to a minimum endpoint. So that's also the empty set. Now, f is increasing on. Well, it looks to me like if I work from left to right, this graph is always increasing. So it is increasing within its entire domain. X is in, and you can just rewrite the domain, or you could write within its entire domain. Okay, I just rewrote the domain there. I think on the test I'm going to have you either circle within its entire domain or the empty set if it was never increasing. Now, when is f decreasing? Well, this line is never decreasing, so this one would be x in the empty set. So on your test, you're going to have the option of circling within its entire domain or the empty set on each of those. And then the y-intercept and the x-intercept. Well, the graph has a y-intercept. And this is cool because when they ask me for intercepts, if they exist, I already know one of the coordinates. At the y-intercept, x has to be 0. And what's the y of that point right there? That's a -3. So there's my y-intercept. Now for the x-intercept, the x has to be 0, or the y has to be 0. See how the y is 0? And what is the x-coordinate of that x-intercept right there? That looks like I'm going to approximate to be 1.5. There you go. That is the features of that graph right here. Is it a function? Communicate the domain, the range, the extrema, increasing intervals, decreasing intervals, and your intercepts. Okay, on the third side of the Module 3 review on this third slide, we have problems 3 through 10. And we are told that approximations are appropriate to answer any of these questions. So sometimes we're going to have to approximate. So, number 3, what is f of 2? Well, this 2 would be my input, so I look at the graph where x equals 2, that's right there, and then I slide down to find my output. It's a little bit off the grid. Okay, so I'm going to have to approximate what that would be. Look at this, -4, -5, -6, I think that's about -7. So I'm going to say that f of 2 equals, and again, I'm going to go ahead and write the ordered pair right here. When x equals 2, y equals -7. So f of 2 equals -7 in function notation. Now remember too, this is function notation for x equals 2, y equals -7, and this is an ordered pair saying the same thing. The x is 2, the y is -7. Next, For what values, if any, does f of x equal 3? So now f of x equals 3, they've given me the output of 3. So I go to my y-axis at 3, and I need to know what point on this graph has a y value or a y coordinate of 3. That point right there. So I'm looking for the x. What's the x coordinate of that point? -3. So f of -3 equals 3. What is the x-intercept? So you guys know at the x-intercept, y would have to be 0. So I have the ordered pair something, comma, 0. And then I just look at my graph right there for the x-intercept. It's actually, there's the x-intercept. What are the coordinates of that point? Well, the x-coordinate is -1, -2. We'll approximate that, about -1.5. And the y-coordinate is 0. So there's my x-intercept. What is the domain? Well, you guys, I love it when I have an arrow at both ends of this line. That means I'm going forever to the left and forever to the right. And this is continuous, so I have to use my interval notation, comma. What is my left bound? Well, this will go to the left forever, -infinity. There is no bound. How about to the right? Forever, positive infinity. There is no bound. And if I cannot reach -infinity, I must use a parenthesis. If I cannot reach positive infinity, which I can't, I must use a parenthesis right there. So in your test, you're going to have boxes for your bracket or parenthesis and your endpoint. And you'll see the comma right in between. Very cool. Okay. On what intervals is f of x greater than 0? Well, look at the part of this graph that's above y equals 0. F of x greater than 0. That'd be that part of the graph right here. So now I'm essentially doing the domain of the blue part of that graph. All right. So x is in. It's still continuous, interval notation. So let's go comma. Am I bound to the left? Well, I'm going forever to the left or approaching -infinity. And what's my bound to the right? Well, it's that open dot right there. What's that x value? Again, approximately -1.5. Then I ask you, can we ever reach -infinity? No, we cannot. So I've got to use a parenthesis. And do you see the open dot? All right, f of x has to be greater than 0. F of x equals 0 when x is -1.5. So that's a boundary. That's why it's open. So we have a parenthesis right there too. Now, on what intervals is f of x increasing? Well, like the last graph, this is never increasing. It is always decreasing. So it's never increasing. So x is in the empty set. Never. On what intervals is f of x decreasing? X is in, and it's always decreasing. Or I could simply say it is decreasing within its entire domain, which means I'm just going to rewrite the domain here if you guys don't mind. And the domain was the open interval from -infinity to infinity. That's all real numbers, you guys. Okay? For what values, if any, is f of x greater than 3? Well, remember when we did the f of x is greater than 0? And we had the blue part of the graph with the open dot. Now f of x has to be greater than 3. So we'll put an open dot where f of x is 3 and work up from there. So now this looks very similar to when f of x is greater than 0, parenthesis, -infinity to -1.5. But now my endpoint is going to be that -3. So let's get there one step at a time though. X is in. And remember, you have to write the red part here. Parentheses, continuous. What's my bound to the left? Well, the graph is approaching -infinity to the left. What's my bound to the right? That open dot is x is -3 to the right. And because we can never reach -infinity, we need a parenthesis. And open dot, we can never reach that -3, so parenthesis on that side. Okay, this is the last problem of the review, number 11. Model the table below, which represents a continuous function with a graph, and they give you the grid for the graph there, a recursive function, and an explicit function. So this is a review of modules 1 and 2 right here. Let's see where we are. Okay, well, you don't have to do this, but didn't we always begin all of our problems in Module 1 and Module 2 with a sequence? And we do that because that helps some students see the pattern of change much more easily, to see if we're linear or exponential, to see our common difference or our common ratio. So the sequence would be these y values in the table: -5, -7, -9, and so on. I see the pattern right there, so I stopped. All right, cool. We're going to use that in a second, I think. But let's go ahead and do the first part. Let's do our graph. So let's plot the first point when x is 1, y is -7. So your x is 1 and your y is -1, -2. What did I say? -7. That's actually a -5. -3, -4, -5. Right there. Okay. Let's plot the second point. Now x is 2 and the y now is -7. -1, -2, -3, -4, -5, -6, -7. Now I could keep plotting these points with this pattern and go from there, but again, they told me this is continuous and 2 points determine a line, so I could do my line right now. But before I do that, let's talk about what we see. I hope you guys remember that the common difference in a sequence is the same thing as the slope of the line. So the common difference, what's happening here? We're dropping by 2 every time. The common difference is -2. You see that in the sequence or in the y coordinates in the table. -5 minus 2, -7. -7 minus 2, -9. -9 minus 2, -11. Or let's do the slope between these 2 points. My rise, I'm dropping 2 minus 2, and I'm running 1. There you go. So either way, the common difference equals the slope, and the slope is -2. That's going to help me with my functions, both recursive and explicit. So here's my graph. Finish it off. I just pulled out my ruler. I began at my first point and went through the second point and put an arrow to go on forever and ever. Recursive function. All right, remember our 4 doors? F of what? Well, what's my first x value? That 1 right there. And what does f of 1 equal? -5. And then f of x equals, I usually have you guys fill in this door. It's always f of x minus 1 to represent the previous output or the previous y. And what did we do to the y every time to get the next y? That's called our pattern of change. That's right, we subtracted 2. It is the common difference or the slope. So there we go. There's my recursive formula. F of 1 is -5, and f of x always equals f of x minus 1, the previous term, minus 2. Now we only have one more part, the explicit function. Okay, well, we don't have a y-intercept, so we're going to have to use point slope instead of slope intercept. And there it is right there, y minus y sub 1 equals m times the quantity x minus x sub 1. All right, so with that, I only need that first point right there. We could use any point. I'd always use my first point right there. So here we go. Y minus y sub 1. This y sub 1 means, what is the y coordinate of the point I'm using? -5. So I'm going to write y minus -5 as y plus 5. Okay, then my slope. Well, that's that -2. I'm dropping 2 and running 1. And then minus x sub 1. Well, what's the x coordinate of the point? I'm using 1, so that's going to be an x minus 1. So here we have, they gave us a table for a continuous function beginning at the point x equals 1, y equals -5. They asked us to graph it. This is the perfect graph over here on the right. They asked for our recursive formula, the 4 doors, remember, and then the explicit formula. And on the explicit, we had to use point slope instead of slope intercept because our first point was at x equals 1. We did not have an x equals 0, meaning we did not have a y-intercept. All right, you guys, thank you very much. I hope you enjoyed this presentation. And study, study, study. Let's be ready for our test.